Okay, we've turned on the recording. Now, I made a mistake last time, and the notes got lost. So unfortunately, there aren't any physical traces of last week's class whatsoever. Anyway, let's okay, let's begin. Well, I'll briefly review a couple of things which we covered at the end of last week's class. Well, last week we defined an orientation of a vector bundle with respect to a cohomology theory. Well, let's recall that an orientation is a choice of a Tom class. The idea is the same as for the usual cohomology theory, meaning we need to choose a cohomology clause such that its restriction to each fiber is a generator of the cohomology group of this fiber as a module of the coefficient ring of the theory. Basically the same argument as for the usual cohomology theory allows one to prove the by the way, let me denote the base of the bundle X. Then we have the isomorphism, which is given by capping with the Tom class. And that's where
что такое здесь хи0?
Что такое? Well, E0. Well, that's a good question. E0 is well, meaning the total space of E minus the zero section.
Okay, thank you very much.
You're welcome. Hold on a moment. Again, the theorem is completely similar to the usual Tom isomorphism theorem, and today I wanted to discuss a few applications of this theorem, and then talk a little bit about complex-oriented theories. Okay, so the well, one advantage of this notion is that it allows one to state and prove the topological version of the Riemann-Roch theorem. and we'll later on today we'll see how one can remember what the algebraic the version the version you may be familiar with from algebraic geometry can be well, at least well, there's a way to remember the version from algebraic geometry by looking at the topological version. Although there is no way that I'm aware of to prove one using the other. Okay. Well, suppose we have H and K two multiplicative cohomology theories. Which in the standard Riemann-Roch theorem will be the K theory of some type or another, and the cohomology theory mod Q with Q coefficients. And suppose the vector, suppose we have a vector bundle called E over X, which is both which is oriented with respect to both theories. And suppose we have a multiplicative natural transformation. Well, later on, not much later, really. In a few minutes, we'll see what exactly this means. Then we can form the following diagram. Hold on a moment. This person calling me a second time. Maybe it's something urgent. Данина, здравствуйте. Если очень коротко, у меня еще занятие. Да, я знаю. Пусть он мне напишет e-mail. Нет, ну не обязательно сию секунду, потому что сию секунду я все равно не смогу ответить. Значит, пусть он мне напишет e-mail. Нет, на мою официальную почту в Высшей школе экономики. Не обязательно сейчас, значит, ну пусть напишет. Я не понял. Ну, в общем, это, конечно, хорошо, но я думаю, что это не, в общем, это не ускорит и не затормозит. В общем, пусть Константин напишет мне e-mail. Не за что. До свидания. Sorry about that. We can form this diagram. This diagram does not quite commute. But it does commute if we replace tau by tau prime. By the Todd class if we replace tau by tau prime, where tau prime of x is tau of x times the Todd class of E. Now the Todd class actually depends on not just E, it also depends on tau, but very often will will write only E to simplify the notation. Now, what is this class? Is the image of 1 under this composite map. Let's see a simple example in which we can calculate the Todd class straight away. Let's take the cohomology mod 2 as both H and K, and in this case we have a natural transformation from H to K, given by the total CNOD operation. It follows from Cartan's formula that this is indeed a multiplicative natural transformation. Well, let's see what happens to 1 after I apply this transformation and the Thom isomorphisms. Okay, so first I apply the Thom isomorphism. 1 goes to the Thom class. Then well, the Thom class goes to the sum of all CNOD squares applied to the Thom class. And then I apply the inverse of the Thom isomorphism. And what I get is the total Stiefel-Whitney class. So as a result, the Todd class, by the way, I need to write the name. So the dotted plots may very well be non-zero, or not equal to 1 either. Okay. Now, are there any questions? Comments or criticism? Well, let's prove the theorem. The proof is completely straightforward. Let me write the proof on the same page using a different color. All maps well, let me be more precise. Not all maps. We basically want to calculate this composite map. First, we go up, then to the right, then we go down. And the remaining map is basically a map which we need to find a formula for. So these 3 arrows are maps of modules over the cohomology of X, and moreover the K cohomology of X is a free module over itself, and it's generated by 1. So to calculate a map of modules, it suffices to calculate this map on on a generating set. Well, I have a preferred generator 1. If I applied this diagram to this preferred generator, I get the dot class by definition. Now, all other elements, the images of all other elements are recovered by using linearity with respect to k upper star of x. Are there any questions?
Why tau is a map of modules?
Well, yes. So here we come to the to the question: what is a multiplicative transformation? So let's let's state the definition. Or well, actually, the proper definition is probably, or at least a better definition would be to say that the structure map of the corresponding map of the ring spectra is compatible with the multiplication, at least on the homotopy level. But we may as well use this more concrete version, which says that tau is compatible with multiplication. Now let's go back. to this diagram. If we now take shall we say the unit disk bundle as X, the empty set as A, and the unit sphere bundle as B, we get exactly the consequence that the map tau here at the top is a map of k modules. Now let's look at this arrow. Well, this arrow is a map of k of x modules by definition. Now let's look at this arrow. This arrow is a map of h of x modules, so it's a map of k of x modules. So the inverse is a map of k of x modules too. Does this make sense? Are there any other questions, comments, remarks? Well, let's see. So to state the next version of the and by the way this statement is what some people call the topological Riemann-Roch theorem, or at least one of the versions. There will be another version, which is which resembles more the theorem we are familiar with from algebraic geometry. But to state it, we need to define the wrong-way map in cohomology. Well, first of all, recall the usual definition of the wrong-way map in for the ordinary cohomology theory. Well, suppose we have a map of manifolds which are oriented in the usual sense, compact without boundary. The wrong way cohomology map is as follows. We first dualize then we apply the push forward map in homology, and then we dualize again. Well, we don't know we don't know what the Poincare duality for general cohomology means. So let's give an alternative construction of this map. Which will also be more more convenient for our purposes in the sequel. So the alternative construction. Well, suppose both x and y have been well, first of all, suppose both x and y are smooth. And suppose we've chosen smooth embeddings of x and y in some high-dimensional sphere. Moreover, suppose the normal bundles of both embeddings are orientable with respect to some cohomology theory. which may be the usual cohomology theory, in which case we'll recover this this construction. And moreover, we can suppose that the map that the map f from x to y is oh, sorry, it's supposed to be a neighborhood of y. Can be represented as follows. We first embed we first embed x in a tubular neighborhood of y, and then take the projection. Then we can do the following thing. We start with the cohomology of x. Then we go to the cohomology of some tubular neighborhood of x. Then we go to
A tuple neighborhood of x is homotopy equivalent to x.
Well, okay. Let's yes, yes, that's a good remark. Well, we need to collapse something. Let's put the boundary here. And by the way, the word Tom written here sort of indicates that we want to consider some kind of Tom space. No, sorry, DUY. So the so I'll explain the map in the middle in a minute. Now, before we do, let's write another word, Tom. Okay, so I take a composite of 3 arrows. The ones on the right and on the left are just the Tom isomorphisms and the universe. Okay, what's the map in the middle?
Ну, отображение инфинитизимальной окрестности, стягивание дополнения до инфинитизимальной окрестности x.
Значит, отец, спасибо, но значит, был такой риторический вопрос, значит, с тем, чтобы как-то все участники задумались. Вот, если это хорошо,
ну, так нужно, чтобы хоть кто-то ответил, нет?
Вот, нет, ну хорошо, но, значит,
но не я.
Я больше беспокоился по поводу остальных участников. Потому что ты понимаешь,
не, ну ты, чтобы ты не заскучала.
За это я более-менее спокоен. Well, it's
просто грустный такой иногда спрашиваешь. Вот,
so well, it's always comforting to know that that someone understands what this thing is, but the thing is, does everybody understand? Well, let's look at this map in more detail. In other words, we have a map from from one Tom space to or at least on the level of cohomology from one Tom space to the other. Well, let's try to draw a picture. So we have uy, and inside it we have y. And then we have the y is shown in red. And then we have x. And well, there's not enough room to show the whole of ux, but let me show at least part of it. Okay, so ux is assumed to be inside the interior of uy, meaning the closure of ux is inside uy. Now we want to construct this this map. How do we go about this? Well, to do this, we need to use the excision property a few times. Let's look at the group on the left. So this thing by excision is isomorphic to the cohomology of the sphere with the complement of the neighborhood collapse. Well, by the same principle, we use excision to to describe the target group as the cohomology of Sn with the complement of the neighborhood collapse. Well, one neighborhood is inside the other neighborhood. So we have the opposite inclusion for the complements, namely Sn minus ux contains Sn minus uy, and and this gives me a map of pairs and the map of pairs induces this this map which we're after. Are there any questions? Okay, so we have explained everything in this composition. Well, exercise prove that for the usual cohomology theory, this construction agrees with the one given by the Poincare duality. And the remark more precisely a question. I don't know the answer to this question. In the second version, we did use smoothness. where? Well, we use it when we said that that the neighborhood of X is homeomorphic to a neighborhood of the zero section of the normal bundle. And in general, the answer is if X and Y are just topological manifolds, then the answer is no. And by the way, Vladimir, it's related to the question we talked about on Saturday. The answer is no, because the signature of the E8 manifold is 8. Which does not divide 16. But on the other hand, one can ask
I'm sorry, answer is no to which question?
Let me finish writing this thing, and then we'll go back and see the question again. So the question is, are there other assumptions apart from smoothness for which make sure the second construction works? Okay, let's go back to the question mark. Yes, it's a question. I don't know the answer. The question is there a version of the second construction which works for at least some non-smooth manifolds, meaning topological manifolds X and Y. And for general topological manifolds, the answer is no. And this follows from the.
Sorry, I don't understand. What follows from existence of manifold with E8 pairing?
Yes, well, there's a manifold
which is not smoothable, right?
there's a very pathological four-dimensional manifold.
Yeah, and what exactly follows from non-smoothability?
Nothing follows from non-smoothability, but there are several things which follow from the fact that this manifold is spin.
Right.
And,
Yes.
more precisely, the second Stiefel-Whitney class well, hold on, we need to be careful because
yeah, but I don't understand if we compute index of Dirac operator for such statement. What is Dirac operator if it's not smooth?
Well, exactly. There's there is well, there are several ways to prove the Rocklin signature theorem. One way is to calculate the index of a certain operator, which is always an integer. And again, it works for smooth manifolds. Another way would be to calculate another way would be to apply the second version of the topological Riemann-Roch theorem, which we haven't stated yet, but we will shortly. To the basically the class of the trivial bundle in the real and not complex K theory. And
Yes.
in order to do that, we need to we need to have this this construction of the wrong way map for cohomology, which uses the smooth structure. We need to have some vector bundle on the manifold such that there is a small neighborhood homomorphic to a neighborhood of the zero section. Okay.
Yes, but I don't understand. The answer is no to which question?
The answer is no. To this question. Is there a second version of the? Is there a version of the second construction, or without assuming that both manifolds are smooth?
Yeah, but still you have a push forward map on cohomology. And
yes, yes. Although it's basically
да, извини, Леш, а имеется в виду, что конструкция какая? Ну, которая на гладких дает тот же самый ответ или просто функториальное отображение?
Смотри, здесь было две конструкции. Значит, первая через
Нет, это я все понимаю. Ну, как бы ты строишь отображение между когомологиями, да, в обратную сторону. Что ты хочешь от этого отображения?
Значит, я хочу, чтобы был изоморфизм тома между многообразием и какой-то трубочной окрестностью, которая была бы там окрестностью нулевого сечения к присвоению. В случае, когда многообразие гладкое, мы берем нормальное расслоение.
Не, я все понимаю, но как бы вот это, ты сам вопрос как бы вот этот можешь сформулировать, что существует отображение F со звездочкой снизу между когомологией.
Нет.
Такое что?
Значит, смотри.
Или ты хочешь как бы...
Значит, я хочу... Нет, просто отображение F со звездочкой снизу, оно, по-видимому, существует для любых теорий когомологии. Значит, но здесь есть... Well, I'll explain. I'll try to explain in English. There's... well, the first construction of the wrong way map, which uses the Poincare duality, seems to work without any smoothness assumptions on X and Y. Why? Well, there's a proof of the Poincare duality in particular in the Adams book, which uses which works for topological manifolds. So this construction works for arbitrary topological manifolds. Now the second construction works for smooth manifolds, and the question is there a way to generalize it to some other types of manifolds? Which are not necessarily smooth, but let's say are homeomorphic to CW complexes, or homeomorphic to simplicial complexes.
So you mean in particular, is it true that for example, our E8 manifold, for some embedding of it in Euclidean space, its tubular neighborhood is tubular neighborhood of some vector bundle, right? Or what?
Yes. Well, well, for Re8 manifold, I think the answer is no. There is no genuine vector bundle on this manifold such that there is a tubular neighborhood of an embedding homomorphic to neighborhood of the zero section. But maybe under some extra assumptions, this is true. Okay, I think we need to have a break. Am I right? Are we supposed to have a break now, or in 10 minutes? Nobody knows. Well, I suggest we take a short break, 20 minutes, and then we'll continue. Okay. By the way, are there any questions, comments, criticism? Okay. So break until 2:40. Okay, and then we'll continue. Well, okay, let's begin the second half. Let's see if the recording is running. It looks like it is. Maybe it isn't. Let's check. Oh yes. Anyway, so the well, the question whether or not the topological Riemann-Roch theorem works for manifolds which aren't smooth is not completely trivial. Because because one of the consequences is the Rochman signature theorem. Anyway, here's the second version of the topological Riemann-Roch theorem. Same as in the first version. Suppose we have two multiplicative cohomology theories. And a multiplicative transformation. Suppose we have two smooth compact manifolds without boundary, such that the tangent bundles are both are orientable with respect to both theories. Okay, let me put the dimensions, although I'll in the next diagram I'll just give those. Then the diagram commutes. Where tau prime of x is tau of x times the top class of mu x in the top row, and the third class of new y in the bottom row. Now
and what is new here? It is like minus
yes,
x.
Where sorry, new x and new y. Of the normal bundles of embeddings of x and y into a sphere, which is sufficiently large. Okay, this diagram will be a part of another diagram which we'll use in the proof. So I'll start a new page. And now I will draw a large diagram. Oh, sorry. This is not tau. Hold on. I'll erase this. I'll erase this. This is not tau. This is tau. Okay. So we have. So we have this this diagram. Let's see. Let's see what is what. Well, the diagonal arrows are the Thom isomorphisms. Well, the horizontal arrows are, or at least the long horizontal arrows are just tau. Now, let's see.
Something's wrong with the indexes, I believe. Because
yes,
the Thom isomorphism should be
yes, yes. Let's not mention the dimensions of x and y, or else the diagram will get messy. Or in other words, all Thom isomorphisms all Thom isomorphisms have degree equal the rank of the bond. So let's look at let's look at this diagram and see which parts of it, which parts of this diagram we know to commute. So there's this part. And the corresponding part at the bottom. And these commute by the first version of the Riemann rock. Now the parts on the left and on the right commute by the definition of f lower Schritt. Of the large square commutes because tau is a natural transformation. So the small square also commutes. Basically, what it says is that if we have a square which is isomorphic to a commutative square, then this first square is also commutative, and this can also be viewed as a version of the Riemann-Roch theorem. Why not? Anyhow, are there any questions regarding the diagram? Well, let's see the relationship with let's see which relation this has to the classical Riemann-Roch theorem. Well, let's take k equal the topological K theory, H equal the rational cohomology. Or let me put it like this. Since I read the asterisks, let me write it like this. H equals the rational cohomology. And tau equal the Chern character. Well, suppose we have a we have X and Y, which are complex manifolds. Well, in fact, almost complex will do. Then all all tangent bundles are orientable with respect to both cohomology theories. Then let's see what the theorem says. Well, the theorem says if I go from K theory to a cohomology, twist the result by the Todd class and then apply the push forward. It's the same as applying the push forward first and then going from K theory to cohomology. CH of F lower star of E times the dotted class of the normal bundle of Y, which is well, these are sorry. So these are just the inverses of the dotted classes of the normal bundle of the tangent bundle. Now there's a discrepancy between topology and the algebraic geometry in the formula for the top class. Now the topologist's top class is the inverse of the dot class in algebraic geometry. So the formula in the end, the formula is exactly the same. There's another thing. Why don't we get the Riemann-Roch theorem from the geometric Riemann-Roch theorem from this Riemann-Roch theorem? Well, the answer is in algebraic geometry. we use the algebraic K-theory. We will prove the algebraic Riemann-Roch theorem if we are able to prove that the push forwards are the same. So the tricky part is proving that this diagram commutes, where the push forward on the left is defined as follows. We take the alternating sum of all direct images. Let's say coherent sheaf. Forget about coherent sheaf. Let's say vector bundle, but algebraic vector bundle. On the other hand, if we're able to prove that this diagram commutes on some algebraic vector bundle, then we're able to prove the Riemann-Roch theorem, the geometric version of the Riemann-Roch theorem for this vector bundle. Are there any questions? Let's look at this diagram again. This statement becomes interesting even if the map from X to Y is relatively simple, such as when Y is a point. let's consider the simple example we saw already. Let's take k equal h equal the cohomology mod 2. And let's take tau equal the total CNOD operation, which is 1 plus SQ1 plus SQ2 plus etc. And we want to prove that the total Stiefel-Whitney class is of X is a homotopy invariant, which means any homotopy equivalence from X to Y takes the Stiefel-Whitney class of the tangent bundle to the Stiefel-Whitney class of the tangent bundle, although we do not require here that the homotopy equivalence should be smooth. And by the way, note that the Pontryagin class is not a homotopy invariant. And besides, well, the rational Pontryagin class is a homeomorphism invariant. But integral Pontryagin classes aren't necessarily invariant under homeomorphisms, and they in some cases they even detect different smooth structures on the same topological manifold. Well, none of this happens when we consider Stiefel-Whitney classes. Well, let's apply the Riemann-Roch theorem and see whether or not it helps. Now, first we need to understand the first we need to understand the map of f lower shriek. Well, it's just a pairing with the fundamental clause. Now let's apply the Riemann rock. Well, let me look at this this diagram again. Here's the diagram. Let me go from let me take a class X here and go and apply the map tau prime. What do I get? Well, I get SQ of X times the Todd class, but we already know the Todd class. The Todd class is the Stiefel-Whitney class of the normal bundle, which is the inverse of the Stiefel-Whitney class of Tx. So this is what happens when I go first to the left. No, sorry, first to the right and then down. The result is the same as when I take X, pair it with the fundamental class, and then basically here y is a point, and this map tau prime is the identity. So I pair X with the fundamental class, and then nothing happens. Let's look at this formula. Does this formula help us in any way? Let's see. Well, it sort of helps, but let's see how. Well, first of all, SQ is invertible. SQ is invertible by the usual geometric progression formula. Note that I don't write any minuses here because plus is equal minus mod 2.
Yes, but we need to invert this as not as geometric progression, right?
Well, we use exactly we use precisely the geometric series formula. Every series, every power series which starts with 1 has a multiplicative inverse.
Yeah, I thought that you want to replace x with SQ minus 1x, so that you left with bare x at the left side of your previous formula. And to do this, geometric progression doesn't help you. You need to apply to x universal inverse of so how to say. But maybe you're right.
Hold on.
You're right. I'm sorry. Everything's fine. Okay. Sorry. So you invert not series with x, you invert just operation. Okay.
Yes.
Ну да, потому что оператор нильпотентен, который к единице прибавляется.
Значит, ну я бы сказал, что унипотентен, но это...
Нет, к единице прибавляется.
Значит, оператор, который прибавляется. Так, значит, здесь, да нет, здесь there's another thing here. Yes, the operations SQI do not necessarily commute. So the stupid formula, which well, the straightforward formula, I think doesn't work. So let me raise this. So let me raise this formula.
No, it's fine.
Не, один-то оператор с собой коммутирует, да?
Yes. Yes, but okay. So let me write it. Let me write it. Let me write it like this, where n is the the sum of well, basically the remainder. Now, now what it says is exactly the same, but the difference is now it's clear. It's more clear why this thing is the inverse. Let's write the formula again. The formula says skew of x w of gx to the minus 1 x it's the same. The result is the same as x paired with the fundamental class. Let's say that this is a skew this is a skew of let's say that this is a skew of y. Now, let's see what we can do with this formula. Okay,
S квад x может быть любым, поэтому подвойственность Степан Карет определяет класс числовик.
Правильно. Ну, давайте попробуем это записать. So what do we have? We have let's say y equal sq of x, x equal sq minus 1 of y. So we have y times y times w of tx to the minus 1 paired with the fundamental class is the same as q minus 1 of y paired with the fundamental clause. So the well, I'm just rewriting this formula using words. The Poincare dual homology clause of WTX to the -1 is given by the right-hand side of this formula. Now let's look at this version and this version. My claim is that they say exactly the same. Does everyone agree? Vanya, do you agree?
Probably.
Say again?
Наверное.
Наверное. Хорошо, тогда давайте разберемся подробнее. Well, the Poincare duality over a field says the following thing. Suppose I have suppose I have a cohomology class, and I want to calculate the corresponding homology class. Well, how do I calculate the homology class? So the dual homology class is uniquely determined by by the following formula. Capping and then pairing with the fundamental bosses is the same as pairing with pairing Y with the dual class. Well, let's see why this is true. Let's transform this as where do I want to put? Let me put. So I transform the left hand side and the right hand side using the gap product, and then I basically use the fact that that homology is a module of the cohomology. And now, Vanya, do you agree with this formula?
Probably.
Okay. Do you agree with this formula, the one at the bottom?
Yes, I agree with everything.
Okay, so this formula makes sense, and the formula right above it is exactly the same. Now, where do I use field coefficients? Do I need to use field coefficients? Does this formula work for Z coefficients? Well, the formula works for arbitrary coefficient ring, but why do I say that K is a field?
Oh, because otherwise Y is not uniquely determined by this formula.
Yes, exactly. K if we have here Z coefficient, for example, then knowing the pairing with every cohomology class does not uniquely determine a homology class, and vice versa. so the let's so the left-hand side, by definition gives me, or not by definition, by this remark gives me the Poincare dual of w to the minus one, and the more precisely, it gives me it gives me the value of the pairing of the Poincare dual homology class with every cohomology class. Basically, I apply the right-hand side of this formula, and then well, we know that SQ and both SQ and the Poincare duality are homotopy invariant, meaning a homotopy equivalence homotopy equivalence takes Poincare dual classes to Poincare dual classes. Does this make any sense? Okay. Are there any questions, remarks, comments, and so on? Well, let's talk a little bit about the about complex-oriented theories. Well, a theory is complex-oriented by definition if gamma 1 over CP infinity is H-oriented. Then my claim is then every complex vector bundle is also H-oriented. Moreover, maps of complex vector bundles are compatible with the orientations. Let's see what happens. Unfortunately, I don't know a direct proof of this theorem. The only proof I know uses the Atiyah-Hirzebruch spectral sequence. Now let's see if Semyon can tell us a simple proof. Well, Semyon is not there, so he can't. Okay. Let me say a few words about the.
Давай я ему напишу в чатике, так что сейчас он тебе скажет.
Okay. Anyway, we will need the Atiyah-Hirzebruch spectral sequence. So let's say a few words about it. Well, suppose I have H an arbitrary cohomology theory. And suppose I have a local trivial fiber bundle or simply a Serre vibration or a Horowitz vibration. Then there exists a spectral sequence which converges to the H cohomology of the total space with E2 PQ equal the usual cohomology of the base with coefficients in the generalized cohomology of the fiber, and these coefficients in general form a local system. Well, Semyon has joined us. Semyon, can you hear me?
Yes, I can.
Very good. The question was, let's define a complex-oriented theory by requiring simply that gamma 1 over CP infinity is oriented. Now we want to prove that all complex vector bundles are oriented. In particular, we want to prove that the bundle gamma n over the un is oriented. Now, I don't know a simple proof of this, so that's why I started talking about the Atiyah-Hirzebruch spectral sequence. But do you know perhaps a simple proof of this statement?
Yes, the proof using Atiyah-Hirzebruch spectral sequence is the most easiest one that I know.
Okay, so anyway, we will need to talk about the Atiyah-Hirzebruch spectral sequence. So let's briefly well, I've already said what this spectral sequence does.
Well, actually, I guess we have kind of well, we haven't discussed it for locally trivial bundle, but we have discussed the coefficient Atiyah-Hirzebruch spectral sequence.
Well, by the way, this spectral sequence is already interesting when the bundle is the identity map.
Yeah, and we have talked about the special case of this spectral sequence when this bundle is just identity map on the lectures when we have discussed spectral sequence.
Okay, well, the general case is not very much different from this case. Well, another obvious remark. This generalizes the Leray spectral sequence for integral cohomology. Or more generally for cohomology with coefficients in an arbitrary group. Well, I think we need to stop here. And first of all, are there any questions? Well, there aren't any questions, so let me save the result and not repeat the mistakes I made last week. Okay, Semyon, this is where we stop, and so I would say the next logical step would be to prove this claim.
Okay.
And then basically
Well, anyway, we'll need this because, well, for discussions of formal group laws.
So I will next go with to calculate the homotopy groups of the MU spectrum. And what about the oriented Buddhism spectrum? Well, this is a good topic. This would be a good topic for a talk. MSO is more complicated than MU, so it makes sense to consider MU first, and then deduce things about MSO by using well, at least some facts about MU. Okay, are there any questions? So we've done MO. But there were some lucky coincidences. Which allowed us to quickly calculate the homotopy groups of MO. With MSO, our luck runs out, and we need to do some work, and it makes sense to consider MU first because it's easier. Are there any questions? Well, in that case, well, it looks like there aren't any questions. So I'll save the slides, and hopefully they don't disappear this time. And I stop the recording. By the way, I don't know why